So section 14.2 is going to involve area, volume, and center of mass. And if you'll remember, what were we doing in 14.1? Double integrals. And so we're going to be using double integrals in this section. In many ways, this section is going to feel a lot like the last section, but it's going to sort of just add on a different kind of a layer on top of what we're doing. In particular, when we talk about center of mass, that's going to be an application, basically, of this idea of volume. All right, so where we're going to start is we're going to start with the basic idea that we've been working with, this idea of double integrals. So when we're using double integrals, we'd like to be able to use them to solve problems. And in order to do that, we're going to talk about what each of the components of the double integral represents. Just as a reference for what I'm drawing, let me start with, or what I'm explaining, let me draw for us to start with a graph that we can reference. So we're going to draw just an XY axis over here. I'm going to draw two curves. So it doesn't really matter what you draw for the first curve and the second curve, just draw them however you'd like. And then the first one we'll call, the top one I should say, we'll call g sub 2 of x, and the bottom one we'll call g sub 1 of x. And we want to imagine that we were taking in, Calc 1, the area between the two curves, so we need a starting point and an ending point A and B, and we're looking at this trapped area right in here. And what we're doing now in this section, and we talked about this last time, is we're imagining that there is some sort of a surface on top of this, and we're finding the volume between this two-dimensional planar shape in R2 and above, up to whatever that surface is in 3 dimensions above it. That sound fairly like what we were talking about last time? Okay, so when we did this, we set up a double integral, and so we said something like this, that our volume, what we actually ended up finally reducing it to, is that our volume over the area, and I didn't mean area, over our region, of whatever our function is that we're dealing with in 3-dimensional space, could be written in one way, especially with the picture that we've drawn, as the integral from A to B. And then the second integral goes from g sub 1 of x to g sub 2 of x of our function f of xy. And we are dealing with the g1 and the g2 of x, so that's dy in the inside integration. And then the a and the b apply to the x value, so dx is the outer integration. We had set this up last time, right? Okay, so let's talk about what each of these pieces are. Well, this one right here is actually the height of our object, right? That's where we are in 3-dimensional space, wherever we are up in the z dimension. And then you can call either one of these. One of them is width and one of them is length. It doesn't really matter what we call them. Your book is calling the y value the width, and it's calling the x value the length. So I'll go with that, but recognizing that it really doesn't make a difference. So we have length times width times height. We have a 3-dimensional object, so we're getting our area. So what we're going to be doing now is we're going to be using double integrals, and we're going to have to be thinking in terms of the length, width, and height in order to actually calculate what we're working with. And in some cases, it might be helpful to actually draw at least the 2-dimensional region. That's definitely helpful. But it might actually be helpful for you to grab something that's a 3-dimensional calculation, or not calculation, a 3-dimensional grapher, whether it's online or if you have a calculator that actually does it, that'd be great as well, just to kind of give yourself some sort of perspective of the picture. This first picture is not too bad. The second one, I'm going to reference a diagram in your book to kind of give us a helpful way of thinking about it. So first what we're going to do is we're going to do something that feels very much like we did last time. Oops. So the directions are that we are going to use double integrals to compute the area of the region bounded by the curves. All right. Our function that we're going to work with for the first one, or our bounds, I should say, are y equal x squared and y equal x plus 2. And you might be looking at this and feeling a little bit like it sounds awkward because it does say area, not volume. We are going to be calculating area on this one. And let's take a look at how that works with double integrals, okay? So this is maybe a sort of strange way of doing it because we could do this problem that we're about to do with a single integral as well. We're just going to set it up with the double integrals to see how it works, and then we'll sort of expand that idea when we work with the volume in the next problem. All right, so the first thing we're going to do is we're going to draw the image that we are being presented with. That is, we're going to draw the curve for x squared, and we're going to draw the curve for x plus 2. So x squared, of course, is parabola, something like this. And then x plus 2 would be a line crossing the y-axis at 2, so looking something like this. And we want the area trapped between. So we want this shaded in region right here. Now, in order to do that with double integrals, what we're going to do is we're going to integrate, and the outer integration needs to be where these two x values actually start and stop. Because it's the y values that are actually changing in their height based on the curve that we're at. Okay, the x values just move from left to right. Whatever the first x value is going to be the lower limit. Whatever the last value is going to be the upper limit. How do we find the locations where this sort of starts and stops? Yeah, we need to find out where they intersect. How can we do that with algebra? Yeah, you could set them equal to each other. Now, I'm not like too specific that you have to show all the steps of these equaling each other, but this is also not a very difficult one. The ones that I've seen your book do for the most part are ones that actually factor and so forth. If they don't and you want to use a calculator to solve them, or even if you want to use the calculator to find the intersection, that's fine. That's really just not the point of what we're doing here. But you do need to find out where they intersect. This one, like I said, is very nice and clean. It factors into x minus 2 and x plus 1. So my x values are actually what? 2 and negative 1. And of course, negative 1 comes first, and the 2 is coming second. So this is negative 1 up to 2. And the inner integral is going to be the top curve for y, what the height is, the highest value is for y, which would be what equation? Yeah, the line, the x plus 2, right? And then we have the lower equation for y, which would be x squared. And sometimes you will see in your book what they do here instead, just going to let you know, I'll do it here on this particular problem. It's not how I was raised, so to speak, but they actually put y equals just to remind you. These are equations for y, just in case you were getting confused with all the notation. So if you want to use y equals on each of those, you can. You don't have to. And what we're doing is we're finding the area with respect to dy first and then dx second, because the inner equations are with respect to y and then the outer limits are with respect to x. And this is of just the single value, and you can put in the number 1 if you'd like, but there's nothing in there that's a height that we're taking anything of. Okay, it's a constant. So we're going to use the value 1. All right, so what we're going to calculate is that we're going to calculate the antiderivative on the inside first. So this is going to carry on the negative 1 to 2. What is the antiderivative of 1? Y, because we're only working with this piece of it now, right? So this is y, which will be evaluated at x plus 2 and at x squared. So we're going to keep carrying along with us the negative 1 to 2 and the dx. And then if I evaluate each of those pieces in there for y, using the fundamental theorem of calculus, I have x plus 2 minus x squared, right? Now I want to integrate this with respect to x. So what do I get? One half x squared. 1/3 x to the third. And we're going to evaluate this at 2 and at negative 1. Okay, so this is one of those great opportunities to grab your calculator and let it do its thing. Let me actually also remind you, I can't remember if I showed you guys last semester, and since I didn't have most of you in Calc 1 or Calc 2, I wouldn't have shown you there, with the exception of Jordan. Because you didn't take Calc 1 or 2 with me, did you, Taylor?
I took 2 with you.
You took 2. You actually did 2, didn't you, Nidra? You took 2 with me. Okay, so you guys, some of you may have seen this before. Grab your calculator, and I want you to do this for me in y equals. Just put in this equation that you got. We'll do this 2 ways. We'll put in the actual equation that you got right here at the very end, not expression that you got here in the end, in the equation spot for y1, and then go back to your regular screen. So right in there, 1/2 x squared plus 2x minus 1/3 x cubed. Now you can use the table feature and plug in the number 2 and write that down. You can use the table feature, plug in the -1 and write that down and subtract them. You can do that. There's actually a really nice, cool way to do in your calculator all at one time as well, and that's kind of handy as well. So if you've stored these in your calculator, in your regular screen, what you can do is you can write in this, and I'll show you where to find all these buttons, but you're going to just write in y1 of, what was my number? 2 minus y1 of -1. So where do you find y1? Well, you find y1 underneath vars. So you hit the vars button, and then you go over to y variables, y vars. It's a function, so you choose function, and then you select y1. And then it even looks like function notation, right? It looks like f of x. It looks like f of 2. It's y1 of 2 minus y1 of -1. And then it can actually do all of that calculation at one time, which is awfully handy. Did you get an answer, James? 4.5. And you're welcome to leave it as a terminating decimal if it terminates. If it doesn't and you want to, or you don't like that, you can write it in fractional form. It would be 9/2.
Does it just show up like that, or should it add something after it?
It just shows up as y1. You have to put the
Okay.
parenthesis after yourself. Yes,
Perfect.
Good question. All right, so I'm going to show you one other thing. So did everybody get that to work? Nidra, did you get yours to work in that way? Jordan?
Just do this.
Yeah.
That's the next thing I'm going to show. Yeah,
Okay.
but you've got the notation for it already set up. All right, so there's 2 ways. And so I know you've got like a math. Who has that math type text thing going on in their calculator? All 3 of you do. And then maybe you guys don't?
Wait, what do you mean?
Where like, well, we'll see real quickly.
Just like that.
I'd like for you to go back to do this. We're going to do this one other way. So go back into your calculator, into y1. This is more important for if you don't have the math text the way I'm going to sort of present it. But go ahead and put y1 and put the equation before we integrated it. Not the very, very first one, but the one right here in the middle with the box around it, x plus 2 minus x squared. Put that into y1 instead, okay? Now, provided that you've integrated correctly, and that 4.5 and 9/2 is the right answer, which it is. We did it all correctly. We can actually have our calculator also calculate a definite integral. So how do we do that? Well, we hit math number 9. So back in your regular menu, after you've put that in y1, hit math 9. And when you hit math 9, it'll either pull up, it'll look like an integral, or it'll write something in your main menu that says function integration, like FNINT. Who has FNINT? Taylor, you do. James, you do. Nidra, does yours say FNINT, or does it have the integral symbol? I know, I saw Jordan's, his has the integral. Number 9, I think yours is going to FNINT. Yeah. Okay. Wow, we're totally segregated today. You half don't have it, and you half do. All right, so if you've got the notation, I don't think you need my help for the most part at all on how to calculate this. But for you guys, just the notation for what you're going to do or what you're going to see is it's going to look like this. Let me write it over here on the side. So you've got the FNINT showing up right now on your screen. You have to tell it the equation you want. Well, we called it equation y1. So you type in y1, so vars, y vars, function y1. And then you have to put a comma. The comma is near the top of your screen. You have to tell it the variable you're using. Our variable is x. And then you put the lower limit, -1, and the upper limit, +2. And so what it will do is it will calculate the integral, where the equation is y1 for the variable x, with a lower limit of -1, upper limit of 2. It's just programming language of the older versions of the calculators. And Taylor, yours might have the ability to be upgraded to that other version. I don't think the 83s will. So we can look at it afterwards because I'm not sure how to do it, but I think I can figure it out. Okay? All right, so that's another way to check out your answer. So cool calculator stuff, right? Okay, so the question might be then, well, what do you want me to show you if I can do lots of these fun, cool things on my calculator, right, Caleb?
Right.
Yeah. So I want to see this last step where you actually integrated. Okay. So basically, I want to see what's on my screen right now. I want to see that you have the integration down there correctly. In particular, I want to see in the middle here, we're about to do another problem where we are going to have to actually integrate with respect to x and with respect to y at separate points. And so those integration steps are going to be present, okay? But the calculation of plugging in the numbers, we're beyond me caring about seeing details about that, okay? Sound good? All right, let's do another example where we're actually calculating volume because that's a little trickier. All right, so we are going to compute the volume of the solid bounded by the given surfaces. These actually are all surfaces. They could be lines as well in some cases. But this particular one is all surfaces. So our three-dimensional shape, if you will, surface is 2x plus 3y plus z equals 6. And the 3 coordinate planes. So the first thing we need to talk about is what are they referring to when they say the 3 coordinate planes? Yeah, so the plane, where basically where x is 0, the plane where y is 0, and the plane where z is 0, or the xy plane, the xz plane, and the yz plane. I think I got them all in there right. So we have, like the corner of the room, basically. That's what we're looking at. We're looking at a cornered shape. And then we have this surface, 2x plus 3y plus z. What is this a surface showing? What is this a shape of? You should recognize it. If it were two-dimensional and it didn't have the z here, what would be the shape of this curve? No, it's not elliptical. What, Caleb? Not an ellipse. Definitely not an ellipse. Nothing squared. That's exactly right. So not an ellipse. Taylor, what'd you think? This would be a line, right? Yeah, if I scratch out my z, this is a line. So what happens in 3 dimensions if I have a third coordinate like this? This is a plane. So this is just a plane. So if you imagine having a third plane intersecting at sort of an angle, a diagonal to the corner of the room, what shape do you get? Can you picture it in your mind? It's going to look like a 3-dimensional triangle. Does anybody know what it's called in 3 dimensions? Huh? Pyramid. Not quite. It is a pyramid, but we have a more specific name for it, actually. It's got a triangular-based pyramid, whereas we also have square-based pyramids, right? Square-based pyramids are the ones we talk about in Egypt all the time. It has a special name when it has a triangular
What does it
base.
start with?
T. Oh, you're so close. It's a tetrahedron. Very close, Caleb. Tetrahedron is this shape. And if you have your book with you, actually, if you turn to page 918, there's a picture of this. So I think we've developed kind of a picture in your mind of what it looks like. But go ahead and reference it, because I'm not going to draw 3-dimensionally. Well, this is not going to happen. But they draw a very nice graph of it with beautiful, shading and so forth on page 918. So you can kind of see it. It's not their. It's not this. This is not their curve. Please don't misunderstand. But you can see a picture of a tetrahedron. Okay, does everybody see that? You have that picture in your mind now. Everything good? Okay. Interestingly enough, it's not a tetrahedron, right? But it's sort of got this corner at a right angle business, which is a little different than you might have been picturing when you just thought of a pyramid, right? Because you don't typically think of the pyramid having a corner or being in a corner of a room kind of thing. All right, so we are going to be working with a tetrahedron. So the first thing we'd like to think about is where do these three planes intersect the plane that's the other equation we're given? What are the corners where we get this to happen? And we have three of them.
Where the other two variables?
Exactly. So if we were to let, say, x equal to 0 and y equal to 0, what would the z value be? 6. How about if x equals 0 and z equals 0? 2. And if y equals 0 and z equals 0? 3. So these are the vertices or the corners, whatever you'd like to call them, really. These are the corners of our tetrahedron. All right, now in all cases, what we're going to want to do is we're going to want to draw that two-dimensional surface and the xy plane, okay? So here's x and here's y, and we can use these points that we've just discovered to show the intersection point in 2 dimensions on the xy plane. So, and I should say that we also get, the corner here at this corner right here. We get that one for free. We didn't have to worry with that because that's where the x, y, and z planes intersect. Okay, so where do we hit the x-axis? At 3. Where do we hit the y-axis? At 2. So my two-dimensional shape actually looks like this, right? And it is a triangular base, just like Nathan said earlier. What's the equation of this line? We're going to need that. We aren't given it. I'm fully confident you can get this. Negative 2/3
X plus 3.
plus 2, right. Negative 2/3 x plus 2. Okay, so what we're going to do is basically what we did in this last problem first. We're going to set up the limits of integration. We'll worry about the thing that goes inside the function in a moment. We're just going to set up the limits of integration. So our outside limits of integration, what are my limits on x? 0 to 3. What are my limits on y?
0 y equals x.
Perfect. 0 to y equals negative 2/3 x plus 2. Now, there's really, we're going to draw a picture of one of these a little bit later that's going to be a little more tricky to see. But basically what we're doing is we're taking this rectangular area, right? So we're going from the top down. On this particular one, we could have done our rectangular, like this representative rectangle, the other direction, and it would have worked just fine. In other words, we could do this one where it integrates from 0 to 2 for y, and then the integral from x goes from 0 to whatever this solves for in terms of x equals, and put that value up here, do x on the inside and y on the outside. We could do that on this problem. This is very clean to do either way because it's a nice, simple geometric shape. Most of the shapes we're working with aren't going to have that flexibility. It's not going to be quite so clean and easy. But this one, we could do it in that way, and it would be fine. All right, so either of the directions, this is the way we did the last one, so we were sort of naturally led down that direction. So we'll do dy and then dx. And then the question is, what goes inside? Well, what is supposed to go inside? The height. The height is what's supposed to go inside. Well, how can I get an equation for the height? Yeah, I need to solve my original equation in the problem, this original plane, for z. And if I solve that for z, I will have my height. So what does that give me?
6 minus 2x minus 3y.
Fantastic. 6 minus 2x minus 3y. Now we need to integrate. We need to integrate with respect to which variable? Yeah, somebody said it, y. All right, so what is my integration with respect to y? My integral. Perfect. Is that what everybody has? Oh, I missed one. Sorry. Mine's not perfect. Yours was perfect as you said it. How about that? Is that better? And we need to evaluate this at negative 2/3 x plus 2 and at 0. And that's where things start to get messy algebraically. And this one isn't even all that bad. They're going to get worse. Now, I'll tell you what, I like the evaluation at 0. That's friendly. But the evaluation at the negative 2/3 x plus 2 isn't going to be all that friendly. So I need to substitute that in for every y value. So I'm going to have 6 times negative 2/3 x plus 2 plus 2x times negative 2/3 x plus 2 and negative 3/2 times, and this is the worst part of it, right? 2/3 x plus 2 squared. And pardon the fact that I've run out of space to now write dx. So we'll write below. Okay, so you guys know how to simplify that, correct? So can I avoid simplifying it with you right now and just recognize that when you're doing it in your homework, this is the part that's going to be kind of messy, but it's still doable from an algebra perspective of things you've done before? Can we just jump to the solution at this point for there? Okay. So what we have at this point then, whoops, is we have still the integral from 0 to 3. And I end up getting 6 minus 4x plus 2/3 x squared dx. And I'm going to write in here that when you're working this out, there's some missing algebra that we recognize that we would actually have to do, and we're just sort of skipping that step for the moment, but you're going to have to do that on your own when you work the problems out. Okay, so now we need to integrate again, right? But now with respect to x. So what do I have for my integral with respect to x? Six x. What's next?
Minus 2x.
2x squared. And then 2/9 x to the third. And then we're going to evaluate all of that at 3 and at 0. And the reality is evaluating that at 0 gives me 0, so I don't have to do much with that. This would be one of those cases where flat out just grabbing your calculator and putting the 3 in each of those x places would probably be your quickest way to do it, not plugging in y1 minus of this minus that. It's not probably all that helpful on this particular one. So if you evaluate this at 3, what do you get? It is, it's 6. You get an area, or volume, excuse me, of 6 cubic units. Any questions on that one? So that was a very geometric shape. Now, if you wanted to actually find that shape, there are formulas for calculating the volume of a tetrahedron. So you could actually calculate this one with geometry, right, to verify your answer. However, not all these shapes are so clean and pretty as a tetrahedron. So let's take a look at one that's maybe not quite so clean and pretty. Same directions as the last one. This is number 3, though. Except we are going to have the surface z. The surface says z equals x squared plus y squared plus 1. Z equals -1. Y equals x squared. And y equals 2x plus 3. And we've got a shape that is a 3-dimensional shape bounded by these 4 surfaces. Now the first 2 surfaces are both equations with z in regard to z. So what are we going to have to do with those in order to get the function that we've been working with or need to be working with in this problem? Nope, not going to need to find points on this one. It's a good guess. We had to find points in the last one to get limits of integration. So I'm sort of going backwards in the way I did the last one. Last time I found my limits of integration first and found the function second. This time I'm finding my function first and I'll find my limits of integration second. It doesn't matter what order you do them in. So what is this function going to be? I mean, last time all I had to do was to solve the equation that I was given for z. But I've got two equations now. Any idea of what we might have to be doing?
Look at the answers sheet.
No, but you're getting closer. Imagine, let me give you the two-dimensional question, and you can tell me what you did. In 2 dimensions, there was one point in time when you were calculating this area right here, and you were given one function, y equals something. And then at some point later, somebody gave you two functions. And what did you do when you were given two functions?
You subtract the bottom function from the x-axis.
Yeah, whatever the values you were going from and to, you had to do a subtraction of the upper curve minus the lower curve. The upper area all the way down minus the lower area down. We had this sort of trapped area between two curves, right? The image is the same thing with what we're working on this problem. On this problem, we have two surfaces. The bottom surface is easy. It's z equals -1. So it's just a plane, you know, 1 unit below the xy plane, actually. But we've got the z plane up here, you know, not the z plane, but this other curve, x squared plus y squared plus 1, that is above the x-axis, xy axis, excuse me, not xy axis, xy plane. It's above the xy plane, and we want the volume of that shape all the way down to the z equals -1 plane. So what do we have to do to find that? You subtract. You just subtract the upper surface minus the lower surface. Now, I sort of just told you the upper surface is the x squared plus y squared equals 1, or plus 1, and the lower surface is the z equals -1. Why? How do I know that?
Because
It's squared, so it's going to be positive.
Yeah, all those values that we're getting out of that first equation are positive values, which are going to be bigger than the -1 value. So in fact, it really is completely above the secondary curve, right? The secondary surface. All right, so our f of xy is going to be taking this first higher curve, if you will, and subtracting off our lower curve, which is plane. And that actually gives me what function that we're going to be integrating in a moment. Right. So this is my function f of x, my height, if you will, of my shape. Okay, it's not the height of just one surface, it's the height between the two surfaces. Okay? All right, so that's one of the things we have to get in order to create our function. So basically, in terms of what we've done so far, we have created this part of it. Now we need to find the limits of integration. And again, you could have done this in the opposite order like we done the last problem if you'd like. So the limits of integration on x and y are going to be based on these last two pieces of information. Make sense? So we need to figure out where in the world would our x and our y start and stop at based on this equation. So this says y equals x squared. You guys know what that one looks like. So a picture is going to be helpful probably for many of these. And then we need the curve 2x plus 3, so it's going to be a shape, again, very similar to the one we had kind of last time. I'm giving a sketch, not an accurate drawing. So how am I going to find those limits of integration, or these intersection points? Yeah, you can set them equal to each other and solve. So 2x equals, x squared equals 2x plus 3. So x squared minus 2x minus 3 equals 0, and this in fact will factor, just like the last one. How? X minus 3 and x plus 1. So x equals 3 and -1. So here's my -1 and here's my 3. All right, so now this is a very good example of a place where we really do not want to do the reverse ordering. I really do want the x values on the outside and the y values on the inside. Because if I draw a representative rectangle here, watch what happens. If I draw a oh, that was too thick. Let me try that again. I draw a representative rectangle here, no matter where I draw it, I've got the same equation on top and the same equation on bottom, right? The problem is that does not happen all the time if I go from left to right. If I draw the curve here, the rightmost side and the leftmost side are both equations of x squared, y equals x squared. If I draw it up here, the equations are different. I've got x squared on one side and I have the line on the other side. That is not helpful. We do not want to deal with it that way. And if you remember, we encountered this in Calc 2 when you're doing solids of revolution, disks and washers and cylindrical curves. There are things that just do not work well in certain conditions. So we definitely have a value that we want to work with on this one being on the outside. The last problem we had of choice here, we really don't have a choice. So we are going to go from -1 to 3 on our outer limits, and that is dx. Now my inner limits need to be the y values that I'm encountering. So do you have a question, Jordan?
I was gonna say, if you did have to do it like with the going sideways,
Uh-huh.
you couldn't like switch, would you have to like do the two different ones and add them?
Yes, you would. And I'm not quite sure how you'd handle that. I think you'd have to define your curves a little bit differently because, first of all, you'd have to write them in terms of y equals and instead of having x equals instead of y equals. So you'd end up with like x equals a square root of x and x equals a negative square root of x for part of it as well in order to get that lower piece. Yeah, and it'd be very messy. Yeah. All right, so on my limits for y, what is my upper limit for y? What's the upper curve? Yeah, it's the 2x plus 3. Right? The upper curve is this one right here. It's the line. So now I'm back to drawing my representative rectangle like this. The top shape is, or the top height for y here basically is the line, and the lower height for y is the parabola. So that's the x squared as our lower limit of integration. And again, you can write y equals on those if you prefer. All right, so setting them up is half the battle. The other half is algebra. Okay, the integration is really not difficult. You guys know how to do that one for the most part as well. It looks a little bit funny because we're doing it in two variables, but that's usually not the tricky part. So let's do the integration together. What is the integral for the inside here with respect to y?
X squared y plus 1/3 y cubed plus 2y.
Everybody agree? Sounded pretty good to me. In some respects, this one's cleaner than the last one because I don't have any fractions involved in the plugging in part. The last one I actually dealt with plugging in a fraction because the equation was had a fractional slope. But there's something about this one that's worse than the last one. What is it? I've got a y cubed. That's one of the things. I wasn't even looking at that when I mentioned it. Yeah, that's definitely going to make it worse. There's something else that makes it worse too.
That's the second bottom.
Yeah, the bottom limit's not 0 on this one, so that also makes it worse. I actually have to physically plug in both of those individual limits. Are you guys with me? So I'm going to show the step of the plugging it in, but then again we're going to do this sort of missing algebra notation. Well, you know what books say when they do that? They say left as an exercise to the reader. So that's what I'll say. This is left as an exercise to the student. So I'll show it written in. So this is x squared 2x plus times 2x plus 3 plus 1/3 times 2x plus 3 cubed plus 2 times 2x plus 3. And it should be all of that minus plugging in the x squared value. So we have x squared times x squared plus 1/3 times x squared cubed plus 2 times x squared. And then all of this is supposed to be having a dx on the end. Again, I've run out of space. So my disclaimer right here is that we've got a missing algebra, 2 or 3 steps probably to clean that up. But when we do clean it up, the missing algebra and everything will lead us to have this particular value. So we're still, our integral is going from, is it -1 to 3? It's actually -1/3 x to the 6th minus x to the 4th plus 13x squared plus 22x plus 15 plus 14/3 x cubed dx. Doesn't really look a whole heck of a lot better than the last version of it, does it? It's pretty long. All right, so we're going to integrate now with respect to x. So integrate with respect to x, what do we get? Okay? Mm-hmm. Good.
13
Yep. Right, good. Yeah, unfortunately, over 12 could reduce to 7/6. So eventually you'll reduce it one way or another. And we're evaluating this at 3 and -1. And I really wouldn't want to put all that in my calculator by hand. So if there's, not my calculator, but I would not physically in the regular equation want to actually plug in the 3 and the -1. So using the y equals would be helpful on this one, or even using this original equation right here before it and doing the integration step, because you have fewer fractions to enter, might be a helpful thing to do. If you do go through and evaluate this, just to let you know, you get something very not helpful in terms of an answer. It is the answer, it's just not unhelpful, that's not the right word. It's not very pretty. 22,016 over 105. And with the 105 in that denominator, I'm thinking that this probably does not have a terminating decimal form, so it really does need to be left as a fractional expression. Does that look okay? On what part?
Can you go back?
Sure.
Yeah, that right there.
Uh-huh.
Why is it dy first, or we bring respect to y first?
Because what we did is we did our inside limit with the y value on top. So this y value right here was the 2x plus 3. And this y value right here was x squared. So we talked about taking the upper value for y minus the lower value for y. So my limits for y were what were done on the inside. And then afterwards, my limits for x, where x starts and stops being at -1 and 3, were the outer limits. And we need it to be in that order. Otherwise, if we drew our representative rectangle the other direction, it wouldn't be okay.
But I guess I'm not picturing it right, because the way I see that
Yeah?
is you have a rectangle going up, and then you should have a dx. A small change in x, not a small change in y.
But the upper values are what we're subtracting. So we're trying to find the height of that rectangle. The height of that rectangle is the upper limit for y minus the lower limit for y.
Right.
And that's the piece that we're finding the height for. And your book's calling that width. I don't mean to confuse that issue, but that's with respect to y. Those limits are with respect to y. And it might be helpful also when you're writing it to write down that this right here says y equals 2x plus 3. And this is y equals x squared. So these are functions with respect to y that we're calculating. The other thing that can't happen is, like, let's say, for instance, you got them mixed up and you wrote everything down here right, except for you did dx. You wrote dx on the inside and dy on the outside. The problem with that is that the 3 and the 1 don't apply to y. All right? And even if you weren't sure and you switched 3 and 1 around and you actually put like y coordinates in there or something like that, the problem is that when you substitute this in, this equation, when you solve it, needs to only have whatever variable is at the end that you're working with as the only variable. So I can't, for instance, plug in limits of 2x plus 3 and x squared if the last thing I take the integral of is with respect to y, because now I've got everything in terms of x's. So I mean, it would be in terms of the wrong variable for that to even work. I have one more example, Caleb. Maybe it'll help clear it up. I don't know. But let's try it and see what happens. The last example that I have is actually based on something we did in Calc 3. It's based on centers of mass. So we're working on mass, centers of mass. And in doing that, I want you to remember what a lamina is. So all a lamina is it's a two-dimensional, it's not even say two-dimensional, that's not how your book describes it. They call it a thin, flat plate. In the shape of a region R in the plane R2. So you've got some sort of an image of some kind of shape, and it could be circular, but it could also have some sort of irregular form to it. And it is flat. It's not really two-dimensional. It's flat. But what we're going to be working with is going to be working with having a certain density, and the density is going to change based on where you are in the curve. So certain parts of it are a different metal maybe, so they're thicker, they're denser than other parts of it. What our question is about this, maybe I'll write that down actually too. The density is going to be rho of xy. How dense it is at any particular point is a function of the point location where we're at. And what we want to do, our goal, is to find the mass and the center of mass. And if you'll remember from Calc 3, center of mass is this idea that it's the balancing point. You know, if there is a location that you could put one, you know, if you hold it up on your finger, there is a location where you could hold it up on your finger if you're completely still, and it would balance, wouldn't fall, wouldn't tip in any direction. That would be the center of mass. Okay? So how do we find that? Well, there's a couple of formulas, and these come straight from Calc 3 from last semester. So the mass is found by taking the area over our region, of the density of the object. Okay, so the mass is just, that's just what we've just been doing exactly. And then finding the moment. Okay, I'm going to run a space here anyway. Let me go to this other place. We're going to have the moment with respect to the x-axis. We called that in Calc 3 capital M sub x. And this is the double integral, again, over our region of y times rho of xy over our area of our region R. We have our moment with respect to the y-axis. It's a mirror image of this with respect to y. So m sub y is a double integral over our region of x times rho of xy dA. And then the way we calculate the center of mass is that it is the point x bar, y bar, where x bar is found by taking m sub y, the moment with respect to y, divided by the mass, and y bar is found by taking m sub x, the moment with respect to the x-axis, over the mass. And we had these formulas before in Calc 3, so I don't want to go into too much more detail, but to remind you of them. But now we're going to be using double integrals to do them with respect to volume of an object instead of just a flat out surface that had, what we had before basically is we had a constant density is what we were doing, and now we're doing a variable density. That's the difference. All right, so let's take a look at an example. We'll at least write it down and we'll solve it next time so that you guys have it. So the example is going to be to find the mass and center of mass for the lamina. And our lamina, I keep having stray marks going on today. Our lamina on this one is a lamina bounded by x equals y squared, x equals 4. And the density for our lamina is y plus 3. All right, so I'm going to draw the two-dimensional region because we need that region in order to construct our double integral limits of integration. We already have our function given to us in this problem, so that part's actually quite nice. What is going on in this shape? What is the equation of x equals y squared look like? Sideways parabola, right? We are no longer confined to thinking about functions or anything in terms of it being just up and down. And then I've got this equation x equal 4. What does that look like? Vertical line at 4, right? We'll go with something like that. So this is x equal 4. This is x equal y squared. And our planar lamina is this part of the parabola, right? Now think about how you're going to draw that representative rectangle. What's going to make sense for this one? Sideways. This is what's going to make sense for my representative rectangle, because then I have a constant value that is above the other one. So in terms of setting it up, we'll set up our limits of integration. Our limits of integration are going to actually have, in this case, y on the outside, right? And then x on the inside. Our function is y plus 3. That's our density. And the inside limits are going to be the equations. So in terms of thinking about the bigger x value versus the smaller x value, what is the curve, or in this case lines actually, line or curve, that we actually have as the bigger one? That's x equal 4. So this says x equal 4 on top. What is the value on bottom? Yeah, that's x equal y squared. What am I going to get for my limits of integration on y? Yeah, it's actually 2 and negative 2. If you were to solve this one solves very clean and quickly as 2 and negative 2. So I have negative 2 down here and positive 2 up here. And then from here, we can actually solve this much like we did in the last problems. And I think what I'm going to do is I'll stop this video, and I'm going to put your homework on here so you have it. I'll stop this video. Actually, let me do that the other round. I'm not even going to stop the video. I'm just going to pause the video. I will head back to my office, and I'll finish the little last part of this because there's not much left. There's probably like 3 or 4 minutes left, so that you have that. And then I'll post the homework in it afterwards. Okay? All right, so picking up where we left off, we're going to find the integral of the inside function, which with respect to x would be xy plus 3x. And this is a much cleaner evaluation than the ones we just had been doing before. Sorry, let me get my limits back on there, negative 2 to 2. I want to evaluate this from 4 to y squared, and it's dy now on the outside. So when I plug in these values one at a time, I'm going to get for y plus 12. And then I will subtract, plugging in y squared. So this would be y cubed plus 3y squared. And actually, I don't even have anything that can combine there. I'll distribute the negative, but that's really all there is to do there on that one. So we have negative y cubed minus 3y squared plus 4y and then plus 12 dy. And then we'll integrate that with respect to x. So this would be negative y cubed x. I'm sorry, not with respect to x, with respect to y. All right, negative 1/4 y to the 4th, negative y cubed, plus 2y squared plus 12y dy. And then we'll plug in the number 2, we'll plug in the number negative 2, which I know you guys can handle that. The value we actually end up getting here is 32. Now the tricky thing on this is that found our mass. So we are, in essence, sort of half done with the problem, except that the other half takes longer. So finding the mass is the simple part. Finding the moments are a little bit trickier because the equations are a little bit, they're a little bit more difficult to work with. Not crazy different, but they are different. So I'm going to go from negative 2 to 2. I'm going from y squared to 4, and those are values for x equals, of course. And I'm working on taking m sub x, so this should be y times my density, y plus 3, dx, and then dy. So as I'm working through this, I've actually got a little bit messier equation in the center, expression in the center to deal with. I've got y squared plus 3y that I'm integrating with respect first to dx and then to dy. So with respect to x, just like on the last part of the problem, this actually just becomes xy squared or y squared x plus 3xy. And we're evaluating that at 4 and y squared dy. All right? So I plug in the number 4, I plug in the number y squared, and again, I'm going to kind of skip the algebra in here, so there's not a lot of it, but just for the sake of time here, there's missing algebra. That you would fill in if you're working the particular problem. The result is that I get negative y to the 4th minus 3y cubed plus 4y squared plus 12y dy. And then if we integrate that with respect to y, we have negative 1/5 y to the 5th minus 3/4 y to the 4th plus 4/3 y cubed plus 6y squared. And we are trying to evaluate all of that at 2 and negative 2. And when we do that, we actually get just, you can use your calculator to get this value. You don't have to show this steps out or anything, but you get 128 over 15. Now, the reason we did m sub x was that in having m sub x, we can actually find y bar. Y bar is finding m sub x over the mass m. So m sub x is 128 over 15, and we want to divide by the mass, which is 32, so I'll multiply by 1 over 32, and I end up getting the x bar is actually 4/15 when we multiply and simplify that. All right, one other thing we need to find. So I found out y bar, I need to find x bar for the center of mass, which means finding m sub y. So m sub y is the integral from negative 2 to 2, same limits of integration from y squared to 4. But this time now I need x times y plus 3, dx dy. So this is xy plus 3x that we're taking the integration of. So if I integrate this with respect to x, I'd get 1/2 x squared y plus 3/2 x squared which I would evaluate at 4 and at y squared. And I guess I'm going to jump the gun a little bit here and put that I've got some missing algebra. Please do not just write missing algebra on your work. You do need to have the actual algebra shown out when you're doing your homework, please. And this goes from -2 to 2. And what you actually get when you simplify and substitute that in there is you get -1/2 y to the 5th minus 3/2 y to the 4th plus 8y plus 24 dy. So we will integrate now with respect to y. I get -1/12 y to the 6th minus 3/10 y to the 5th plus 4y squared plus 24y. And we evaluate that at 2 and -2. And when we evaluate that at 2 and -2, we actually get 384 over 15. Not 15, sorry, 5. Look at the right page. 384 over 5. And again, the reason we did that is because then we can find x bar. X bar is m sub y over m. So m sub y, we had just now found, was 384 over 15. And we divide by m, or multiply by 1 over 32, which 32 is the m value. And we actually get that x bar is 12 over 5. So our center of mass, I'll just write it on another screen here in just a moment. So our center of mass, which is the x bar, y bar, just as a reminder, our center of mass is actually 12/5 4/15. And that's the place where we could put a fulcrum and we could actually balance this planar lamina. All right, so the last thing to do then is I will write in your homework. Our homework for this section, it's not due on Thursday, it will be due next Tuesday. Homework is from page 923. It's numbers 3, 6, 8, 11, 14, 17, 28, and 31. So 8 problems.